Hi, hello guys. Hey, it's Tekiso once more. You can see now we are in a very different environment. It's load shedding inside, and at least I was told that this can also be a conducive environment as long as we share information. Today someone wrote to us to ask us to further those induction motors, and he struggled with this problem where you are given the conditions on no load and the conditions at full load, and he wants us to clarify that. This might be a proper more understandable question if you got the solution, but he's more interested in reasoning. That's why we're gonna do this problem. Now let's start. It says a 3-phase 500 volts 50 hertz delta connected induction motor running on load, taking a current of 75 amps at a power factor of 0.8 lagging, and a full load motor speed is 960 revs per minute when running light at 500 volts. The motor input current is 10 amps, and the power factor 0.86 lagging. Remember, it runs load. It means nothing is connected to the motor. There is no load. The windage and friction losses represent 1.5 kilowatts of the total constant losses, with the rotor iron losses negligible. It's 0. If the resistance per phase of the stator windings that is delta connected is 1 ohm, determine the output of the motor and the efficiency of the motor. Now, first of all, that's key. First of all, you must start with the conditions on no load. When nothing is if there's no pump or whatever connected to the motor, there is no load, and you are given what? When running light on no load, of course, let's do this. This is my secret, guys, to do this. I don't know whether you'll see there. I think yeah, it can be. Yeah, yes. This is the output. But remember, this thing runs on no load. Nothing is if there is nothing connected to the motor, there can't be an output. It means the output is 0. But here on the shaft here, you are given 1.5 kilowatts. And then this, it can be calculated. The input power on no load, of course. The input power on no load. Remember, this is the stator. And it is equal to √3 V line load current on no load multiplied by cos of phi. And then we've got √3 multiplied by, you are given 500 when it runs on light or no load. It's 500, and you are given 10 amps on no load. Multiply by 10, multiply by 0.86 lagging. And the answer there is, hey guys, we also race against time. It's load shedding, it's late, but as long as we can share the information, subscribe so that you can be notified and go for yourself on this problem. √3 multiplied by, second function, √3 multiplied by 500 multiplied by 10 multiplied by 0.86 is equal to what? Is equal to 1, 2, 3, 0, 7, 448 kilowatts. This is on no load. And now here, this is the stator. When this 10 amps current enters the stator, it becomes a phase current. But remember, it's what? It's delta connected. It's work from the basics. V line is equal, in a delta connected system, the I line is equal to √3 I phase. We have to find I phase. Therefore, I phase is equal to I line, which is 10 divided by square root 3. Divided by 10 divided by second function square root 3. And it's equal to what? It's equal to 5.774 amps to 3 decimal place. This is the phase current. This is the phase current. Now, this is phase current. The line current has been divided by the square root 3 to get the phase current. So this is the phase current there entering the stator. Now then that we've got the phase current. Remember, the stator consists of the stator copper losses at no load and the iron losses at no load. Now this is equal to 3 multiplied by I squared. But now what is I squared? It is multiplied by 5.774 squared. Multiplied by, you are given the resistance of 1 ohm at light when the motor is running at no load, which is 1. And it's equals to what? It's equals to 3 multiplied by 5.774 squared. It's equals to 100 watts. 100 watts. It's 100 watts there. Now, but here you are given what? You are given the output of this. Now, let me tell you something that I've never mentioned earlier, and that's it's a very, very important statement. The main reason why you are given the no load losses is for you to find the constant losses that were not given for you in order to compute or to perform calculations. That's why in this problem you are given the no load. Now you've got this at no load, the stator copper losses. Also that now you can find the iron loss. The iron loss is equal to what? Is the input power is equal to the output plus losses. But remember, at no load, the output is 0. There can't be an output because the load is not connected to the motor. So this falls off. Now I'm telling you, at no load, the input power is equal to the losses. That's the point I was trying to make. Okay, right. Now it's equals to losses. Now this input is calculated as 7.448 multiplied by 10 to the power 3 is equals to what? Is equals to the losses. But what are the losses? The 1 gauge losses of 1.5 multiplied by 10 to the power 3 plus what? Plus 100 watts plus what? Plus the stator iron losses. Now we can find this. Now the stator iron losses is equal to what? Is equal to, let's see, 7.448 exponent 3 minus open brackets 1,500 plus 100 closing brackets answer is equal to what? Is equal to, say, 1, 2, 3 is equal to 5.84 5.48 kilowatts. 5.848 kilowatts. This, the iron losses there is 5.84 kilowatts. I hope a person who sent this question is watching. Really, this is very easy. Let me tell you something by my friend here next door. There's someone, I'm working with someone by the name of Ipeleng. She mentioned a very interesting thing. She said to me, Tseki, so you know, sometimes people might have memorandums, and when you do something, they say it's easy, but they don't know the reasoning as to why this is the case, how this one is found. So it's important that you do examples as well, or the problems you think they have. Everyone have this problem, but they struggle reasons to give. That's why they only do with to pass, and then after that they forget. Let's do things for understanding, guys. We are sharing this for knowledge so that we can help each other in future. But this is the case. This is the case. Now then that we find this, we can go and calculate conditions at full load. Remember, you have to calculate the output. At no load, the output was 0. And you have to calculate the input, the efficiency rather. The efficiency, which is the output over the input. Now, let's do this. The iron losses is equal to 8.84 kilowatts. And then what? Yeah, that's it. Now let me erase and then do the conditions for full load. Okay, right. All right. I hope we are all happy with this. Conditions for full load. If I do mistake, you shouldn't stress a lot. I have to do mistake. Imagine, aren't you gonna do mistake? What you gonna do if oh, let me leave it for another day. Let me leave it for another day because we are running out of time. Conditions now for full load. Always, guys, I can't perform calculations without doing this. Me personally, and I will advise, not advise, because we are all students of education. I will suggest that we all do this. Always, you are requested to calculate the output there now, and this is the shaft, and then on the shaft you are given 1500 watts. This is the windage and friction losses. You have to go and find Pmax here. Here is the rotor. Here is the synchronous power. If you started with us, we proved these formulas. Here, formulae rather. This is the stator, and then here is the PCU stator, the stator copper losses, and then the stator iron losses that are calculated as what? As 5.84 kilowatts. This can't be the losses of the initial calculations, because now the motor is now connected on load, and there is a current for that matter. There's a current of, this was the current for no load, this is now the current for full load. Right, now for full load, the input power is equal to what? √3 multiplied by, you are given 500. √3 multiplied by 75 multiplied by cos of 5. But what is cos of 5? It is 0.8, not 0.86, but 0.8 on when running on load, and it's equal to what? It's equal to second function square √3, sorry, multiplied by 500 multiplied by 75 multiplied by 0.8, and it's equal to what? It's equal to 1, 2, 3. It's equal to 51.96 kilowatts. Oh, take this 96 kilowatts. Right. This is the input there. But now, this 75, when it enters the status, it becomes a phase current. And we know that in a delta connected system, I line is equal to √3 I phase. And it's equal to what? Therefore, I phase is equal to I line, which is 75. It is 75 divided by square root 3. And it's equal to 75 divided by second function square root 3. It's equal to what? 43.3 amps. 43.3 amps. The current there. Now then that it enters the status, we can calculate the stator copper losses. There, this. The stator copper losses is equal to 3 I squared, which is of course 43.3 squared multiplied by the resistance of the stator, with that which is given as what? S1. Right. And then this is 43.3 squared multiplied by 3 multiplied by 1. And it's equal to what? It's equal to 1, 2, 3. It's equal to 5.62 kilowatts. There, 5.62 kilowatts. The stator copper losses there is 5.62 kilowatts. Now, we've got the input, we've got the stator iron losses calculated from the conditions of no load, of course, and we just calculated the stator copper losses on full load, and they gave us this much. Now that minus this, we're gonna get the synchronous power. The input minus, okay, let me put it, the input which is 51.96 minus open brackets the stator copper losses of 5.62 plus 5.84 is equal to what? The input minus that. Therefore, the synchronous power is equal to the input minus the stator losses will give us the synchronous power. And it's 51.96 minus open brackets 5.62 plus 5.84 closing brackets answer. It's equal to what? It's equal to 40.5 kilowatts. There. This is 40.5 kilowatts. Now, one other thing, very important. If the stator iron losses are not given, the rotor iron losses are not given, they are always or most of the time negligible. That's a rule. If the stator iron, if the rotor iron loss are negligible, therefore, here we are here now. We are here on the rotor. Therefore, the rotor copper losses is equals to the slip multiplied by the synchronous power. But now, what is the slip? What is the slip? What is the slip? Very, very important. You are given what? Let's check first. You a 3-phase blah blah 50 hertz. You are given 50 hertz. Okay, nothing has been mentioned, but let's check what is the slip. Let's check what is the slip. The slip is equal to what? Let's say the synchronous speed is equal to 120 multiply by frequency of 50 over the number of poles. Over the number of poles. Let's check guys. You are giving the rotor speed of 960. If you are giving the rotor speed of 960, we can all agree that the synchronous speed should be nearly close to 960, but just above 960. How do you find it? We are still on the right track. Let's check. This 120 times 50 is equal to, I think it's 6,000, isn't it? 120 multiplied by 50 is 6,000. 6,000 divided by, say, 2. Divided by 2 is going to give us how much? 3,000. Divided by 3. 6,000 divided by 3 is going to give us how much? 6,000 divided by 3 is going to give us 2,000. But 6,000 divided by 4 is 1,500. Let's check. 6,000 divided by 6 is 1,000. 1,000 is close to 960. Why? If we say 7, that's 7. This synchronous speed is gonna be less than 960. So the speed here is 6, and it is 1,000 revs per minute. Mr. Matasan, I don't want to call people by name, but the reason why you were struggling with that, I rest assured, is because of it was this. You are not giving poles and what, but you choose. You say, if I divide 6,000, 120 divided by 50, 6,000. If I divide by 2, it becomes 3. By 3 is 1.4. By 4 is how much? Is 6,000 divided by 4. It becomes 1.5. But if you say 6,000 divided by 6, it becomes 1,000. 1,000 is close to 960. But if you say 6,000 divided by 7, it's going to be less than 960. And a synchronous speed should be above the rotor speed. Now, the slip. The slip is equal to what? It's equal to the synchronous speed minus the rotor speed over the synchronous speed. And it's equal to 1,000 minus 960 is given over 1,000. And it's equal to what? It's equal to 1,000 minus 960 divided by 1,000. And it's 0.04. 0.04. The slip there. Where is the rotor? The slip there is 0.04. Now that slip, meaning we can calculate what? The rotor copper losses. The rotor copper losses is 0.04 multiplied by a synchronous power of 40.5, and it's equal to 0.4 multiplied by 40.5, and it's equal to what? 1.62 kilowatts. Why kilowatts? Because our synchronous power is in kilowatts. So this is kilowatts. Now, this is a done deal. Okay, this is the rotor. Okay, let's say it's 1.62 kilowatts. And then here is 0. We said they are negligible, of course. Now we've got 1, 2, 3, 4. We are done. We are done. I can erase here, guys. Everything is done. It's done. Let's see. Let's see. Okay. Right. Now. We have to calculate what? We have to calculate the output because we've got the input. The input is equal to the output plus losses. The losses is, what is the output then? The output is equal to 51.96 minus, open the brackets, let's sum them all. This is 1.5 plus, this is 1.62 plus, this is the stator iron losses is equal to 5.62 plus the stator iron losses, the stator iron loss is equal to what? Is equal to I think 5.84 the losses, 1 2 3 4, and then of course 51.96 minus, open brackets, 1.5 plus 1.62 plus 5.62 plus 5.84, closing brackets, answer is equal to what? The output is equal to 37.38 kilowatts. That's the output. You were requested to calculate the output of the motor. But now what is the efficiency? That should now be straightforward. The efficiency of the motor is equal to what? The output over input multiplied by 100%. This is equal to 37.38 over the input of how much? 51.96 multiplied by 100%. Therefore, the efficiency of the motor is equal to 37.38 divided by 51.96, open brackets, multiply by 100%. It's 71.94%. You have answered those questions and you've got that 15 marks. That's 15 marks. Guys, I can only do these problems based on what people send to us. Just send your problem, we will do it. We will do it. Someone sent something to do with transformers in parallel. We don't have time. We are working. We are late. It's load shedding. But please just subscribe, share, and comment. We'll meet you again maybe next week, guys. Mwah.